Bateman's infinite series of quadratic equations. My motto? Plain honesty, simple truth, easy understanding. The joy of finding things out for yourself. The simpleton's mathematical coat of arms. The motto? In Euclid we trust. Proposition: that for every integer, odd, even, prime or composite, there is a uniquely associated quadratic equation that, along with its roots, can be directly generated from the integer using nothing more than an electronic calculator to give y equals bx minus x squared minus c. 1. Take the square root of the integer, which for our example is 2671. 2. To the integer part of the root add 2 to give the coefficient of the quadratic equation b, which is equal to alpha plus beta, the sum of the roots. 3. Subtract the square root from the coefficient b and divide by 2, which will give the root alpha. 4. Subtract the root alpha from the coefficient b, which is equal to alpha plus beta, to give the second root beta. 5. Hence the coefficient c is equal to the product of alpha and beta, which gives c equals 34.5. 6. Hence the unique quadratic equation associated with the integer 2671 is y equals 53x minus x squared minus 34.5 QED. 7. The quick way is 2671 minus 53 squared all divided by 4 equals minus 34.5. Therefore, y equals 53x minus x squared minus 34.5. So again, QED. The next two slides contain the first 28 quadratic equations starting with the integer 0. Yes, 0 is both an even number and an integer. Uniquely, you will find that its associated quadratic generates every negative square integer from -1, -4, -9, all the way out to -infinity. Notice the significance of the quadratic equations for the square integers highlighted blue on the equations that result for all the integers between the squares. The outputs of the quadratics for integer inputs of 1 to infinity are initially positive and then turn negative all the way out to negative infinity. The number of initial positive outputs increases with increasing size of the integer associated with the quadratic. The outputs signify orderly decay downwards from the associated integer. Hence, the decay can be used to factorize a composite of two primes, but it requires the same number of steps as trial division and is computationally more complex, and therefore takes longer than the latter.